So here, let me make simple observations about how we can actually do this kind of stuff. Again, notice in this case, looking at carefully, there is two dominant directions, one up and down, and the other one this way on this image. We can look at it and actually create a two-dimensional axis here. And now we want to actually start looking at what we can actually extract out of it. Now recall, when we talked about Fourier transforms, we said that when in a Fourier transform, for every frequency omega that goes from 0 to infinity, the Fourier transform holds the amplitude A and the phase phi of the sine function. That's best represented, and we looked at this before, by this equation, amplitude A sine omega t plus phi. So now we are interested in, of course, representing this so we can actually extract information in axes like this, the two-dimensional axes of an image. Basically, what we do is we can use the real and complex numbers to achieve this. So we would represent f omega as a real part and an imaginary part here. The imaginary part and the real part. So now if I can start representing my Fourier transform in this way, which basically means now it's a vector in an imaginary and a real space, we can start doing things like simple vector calculus or vector arithmetic to be able to compute things like the magnitude and the angle. So the magnitude of the amplitude basically is nothing else but the square in the real part plus the square of the imaginary part over in a square root. And that gives me the magnitude, which would be the A here. And phi would basically be the arctangent or tangent inverse of the imaginary over the real number. So that in essence starts giving us information like we can start computing things like this axis and the angle, and it can also compute, of course, the magnitude of this vector using these types of things. And again, depending on what kind of signal you're looking at and what variables you're looking at, we can start computing these kinds of things for an image like this.